Alright, so in this video we are going to discuss RC circuits. So we're going to have a circuit where we're going to put a resistor and a capacitor in series with each other, hooked up to a power supply. So when we look at the voltage across each circuit element, we have a voltage from A to B across the resistor. I'm using little I because we're going to find that the current is not a constant value times the resistance. So ohms R, V equals IR. And then we're going to look at a voltage across the capacitor, so from B to C. So voltage is equal to Q divided by C, and then we're going to find that this charge is not a constant value. So I'm going to use lowercase to indicate non-constant values. And the reason why they're not going to be constant is because, remember, we're charging the capacitor. So we're putting more charge on the capacitor, so that value is going to increase. But because of Kirchhoff's law, as we go across each circuit element, we have to find that they sum to zero, or that the EMF has to equal the voltage across the resistor plus the voltage across the capacitor. So as the charge on the capacitor increases, there's a decrease in correspondence in current across the resistor. Now, rearranging this Kirchhoff's loop rule equation, I can solve for the current, and the current is going to equal the EMF over the resistance minus the charge over the resistance times the capacitance. So when the current is zero, we're going to find that the equation can be arranged so that the EMF over the resistance equals the full charge over RC. So reducing, because there's resistance, we can cancel out on both sides. We get the idea that the charge is equal to the capacitance times the EMF. So essentially the voltage from the power supply times the capacitance gives us our full charge. So really not much different than this relationship up here. Just that we have a final Q value versus a Q at some point in the charging process. Alright, so returning back to this relationship here, remember current is equal to dQ dt. Alright, and I've just transferred my equation from above down here. And now I factored out a negative 1 over RC. And then I'm going to move the Q minus the capacitance times the EMF to the other side and bring the dt up over here. So now I'm going to integrate both sides. I'm going to integrate the left from 0 to Q, and I'm going to integrate the right side from 0 to T. Now my left side, I've used an integral table, and I've looked up the format in order to establish what the integral will be. So this gives me the left side of the equation here. And then the integral of essentially a bunch of constants in terms of t is going to give you a t back, because when we evaluate for 0, we just get 0 back. And then I'm going to do the exponential raised to both sides so that my natural log cancels out. And I'm left with an exponential here, so we're going to see that we're going to have an exponential decay in this relationship. And then I can bring the negative CE up, add this CE to the other side, and factor out the capacitance times the EMF. So I get this exponential decay, but I'm doing 1 minus this exponential decay. So as time increases, we're subtracting less and less from 1 until we reach this max value of the charge. So you'll see that this fits out front here. So as time progresses, we're going to have more charge on our capacitance. Now we do have to be careful with this. This is mathematically true, but not necessarily physically true, because we don't reach a fully charged capacitor until t actually equals infinity. E raised to the negative infinity is 0. But that isn't what happens in reality, because a charge is quantized. So there's going to be a point where you just need one more electron and it's going to be fully charged and you're done. So that's why this mathematical description of this doesn't quite work perfectly, because charge is quantized. You can't, like you should for an exponential, keep splitting things further and further and further to tiny little minuscule thing, trying to approach the final decay. So we'll see in reality, t does not have to equal infinity in order for the capacitor to be fully charged. Alright, so keeping in mind that current is equal to dQ dt, I took the first derivative of this relationship I just derived. And we get the idea that the EMF over the resistance is equal to e raised to the negative t over RC. So the current, as we talked about below, as the charge is exponentially increasing, the current is going to be exponentially decreasing. And this is once again supported by Kirchhoff's law up here. Now I want to introduce you to one special term called the time constant. And the time constant is equal to the resistance times the capacitance. And so if I plug in, since it is a time constant, so it's units of seconds actually, believe it or not, if I plug in the time constant, R times C, up here for t, I get the exponential raised to the -1, because the RC over RC cancel each other out. So if I do 1 minus 1 over the exponential, I get 0.632. Or the idea that when t equals a time constant, the capacitor is 63.2% charged. And we often use this to describe how quickly a capacitor is going to charge. So the smaller the time constant, the faster the capacitor is going to charge. Now let's talk about a discharging capacitor. So at t equals 0, we're going to have a Q equal to Q naught, so a fully charged capacitor. So our QF before, when we're charging the capacitor, becomes Q naught when we start discharging it. Now to discharge it, we're going to unconnect it from the power supply. So we're going to, in the earlier part of the video, I would have closed the switch. Now we're going to open the switch to disconnect it from the power supply. So now when we do our Kirchhoff's loop rule, there's no EMF here out front. And we just have a negative current times the resistance minus the charge over the capacitance. So rearranging the solve for the current now, we get negative Q over RC. Alright, so once again, I'm going to plug in for the current dQ dt. And I'm going to move the Q to the other side by dividing. Now to be careful here, we're not starting out with 0 charge, we're starting out with full charge, so Q naught. So we're going to integrate from Q naught to Q, where Q is some Q value based upon what the T value is. And on the other side, we're going to integrate from 0 to T. So the integral of 1 over Q in terms of Q is the natural log, so we get Q over Q naught. And then we get a negative T over RC, because when we evaluate for 0, the subtracted term becomes 0. So we're left with this idea that when we're discharging the capacitor, the charge is going to exponentially decay now. And if I take the derivative again, because current is equal to dQ dt, I'm left with the idea that the current is also going to exponentially decay in this case.